Hello, I'm Professor Daniel Cote from Laval University in the Cerveau Brain Research Center, and I'm here to tell you about ray tracing in Python to validate your optical systems. In biophotonics, we make optical systems all the time. Spectrometers, microscopes, even just simple light detection systems. Usually we care about getting a signal first, but very quickly we're faced with the real problems. Is my system optimal? Why is the field of view so small? Could I make it larger? What's the maximum amount of light I could get? Where is the limiting lens in my system? Is there something that is limiting the amount of light that is entering my system? And although the formalism to calculate these things is simple, we tend to go with rules of thumb because the tools, the software tools that we could use tend to be a little complicated for beginners. I'm here to tell you about a Python tool that will help you model your optical design and optimize it.
When we say we're doing ray tracing, we're actually applying Snell's law, or the law of refraction, at every point in space. So if a ray propagates in a homogeneous space or free space, it will keep propagating in the same direction. On the other hand, if a ray is incident on an arbitrary surface, the Snell's law of refraction will dictate the angle of refraction, which we can calculate with the law, with Snell's law, that is Ni sine theta I is equal to Nr sine theta R. So within the paraxial approximation, we can use what's called the ray matrix formalism, where we model the ray and the optical elements as matrices. So there's a set of matrices that are well known for all known optical elements, and we can use those sequentially to transform the ray with a simple matrix multiplication. So really, doing paraxial ray tracing in an optical system is really the sequential application of multiple matrices that represent the elements, free space, lenses, free space, etc., onto rays. So we can calculate the position of a ray if we know the initial position and the initial angle anywhere in the system. This is different from the law of imaging, where we can obtain the position of the image if we have the position of the object. With ray tracing, we can get the rays everywhere in the system. But in real systems, the components are finite and can block the rays. So it's not always appreciated that we can use the paraxial approximation and the ray matrices to calculate where the rays are going to be blocked in the system. So with this, we can find the finite element that limits the light collection, called the aperture stop, and the other element that limits the field of view, called the field stop. We can use the ray matrix formalism even with these finite elements. We just need to propagate each ray individually. So if we have a lens, some of the rays will be blocked and some of the rays will go through. The act of blocking a ray by a finite element makes it impossible to write a single transfer matrix for all rays, because some rays are blocked and some rays aren't. Therefore, we need to propagate each ray individually to see whether or not they're blocked. Without a computer, that'd be way too tedious, and we would not do that. However, with a computer, it becomes trivial. And in fact, many companies have made software, such as Zemax, Code5, etc., to do such thing, to do this ray tracing. But those are not for beginners. This is why we have created a ray tracing module in Python. So what can we obtain from this formalism and from these calculations with this simple Python module? So let's take a look at how we can use this formalism to find all images in a very simple system with two lenses. So if we have an object with a point on that object, we know that all rays coming from this point will be imaged on the same height, on the same point on the image. Therefore, this means that the final height of the ray is independent of the original angle, and therefore the B element of the matrix must be equal to 0. So in a system, when we are looking for the image plane, we are looking for the matrix that will be such that the B element is 0 after a certain distance. Let's look at it. So the simplest example we can do is a single lens with an infinite diameter. So the code with ray tracing is very simple. We import the ray tracing module, and then we create an imaging path. We add a space element of length of 100, a lens of focal length 50, and another space element of length 100. Then we can display the system to see what it looks like. On the graph, we see the object in blue, the image in red. The element in the center is an infinitely thin lens. And we have 3 sets of rays from the top, the center, and the bottom of the element, where from each point we have 3 rays originating from that point that are obviously imaged onto the image. This is a relatively simple example. So let's look at what happens when we have finite diameters for a lens. So here we start with exactly the same thing, an imaging path, but we append a space element and especially a lens or lens elements that have a finite diameter that we pass as arguments to the constructor of the lens element. And after this, we can then obtain the graph for the rays in the system. We have, because of the finite size of the first lens and the finite size of the second lens, we can see that there's what's called the axial ray, that is the ray with the largest angle starting on axis from the center of the object, that is limited by the aperture stop, or AS. On the other hand, from the top of the object and going through the center of the aperture stop, at some point, this ray, called the principal ray, will be blocked by the finite size of some element and will limit the field of view. In this case, the field stop is at the camera where it should be and limits the field of view. The aperture stop is computed essentially by starting from the center of the object and increasing the angle until we hit the limiting aperture. And the principal ray is computed by moving on the object away from the optical axis with a ray that is going through the center of the aperture stop until it gets blocked without reaching the camera. We can also do more than that. We can, if we can compute the position of all rays, we can compute the position for a collection of rays. So if we trace a collection of rays and we compute which rays are blocked and which rays are going through our system, then some of them will be blocked, some of them will go through, and we'll be able to compute the statistics as a function of position at the output of our system. So this will give us the intensity profile and also what's called the vignetting report. I did not discuss the vignetting, but vignetting is the partial blocking of a cone of rays in the system and limits the efficiency of the system. So this is something the ray tracing module can give you. Finally, we have also included many commercial lenses from Thorlabs and Edmund, modeled directly from their specifications and their materials. So to use them, we simply have to essentially use the part number, and we can use them directly in systems, in our own optical systems. But if we hit display on these elements, we get a graph of the element with its front focal length, back focal length, principal planes, etc. We can also get the chromatic aberration graph because we are computing all properties directly from materials, not from a fixed index of refraction. In conclusion, I barely scratched the surface, but we have introduced a ray tracing module in Python that's targeted towards non-expert users. It is trivial to install, easy to use, fast for essentially all calculations, and the code is freely available. You can obtain all the properties from that you would obtain from Parexel calculations, but it also includes the effect of apertures. It will give you an efficiency report if you request one. And you can learn more by looking at the tutorial that we have recently published in the Neurophotonics Journal. The reference is here, and I'll be pleased to entertain any questions if you have any. That being said, the best option is probably to go straight to the web and download the module from PyPI, or read the documentation from Read the Docs, or then again look at the source code on GitHub with the links that are provided below. I also insist that this is a team effort with all the authors that are on the paper: Valérie, Shadi, Elahe, Gabriel, Ludovic, Marc-André, and myself.